Hello ladies and gentlemen, and welcome back to GGS300. So this week we're going to be focusing on the 12th lecture, and actually what we're covering today is inferential spatial statistics. So before we get into the actual content, I just wanted to say very well done on the midterm, and I'm glad to see that many of you took advantage of the ungraded test to prepare you for that. So I'm glad to see that it's been going well for many of you. That's great. Apologies to any of you for the duplicate question that was in there. I've now removed that from the course, so that means that there's fewer maximum marks overall. So you should have seen a very small boost in your grade. So apologies for that. It was just down to a Blackboard uploading error, unfortunately. Also, I've also made the point already on the announcements for the course that essentially I will allow you to drop two of the least well graded assignments that you have. So basically for the coursework section, instead of I think it's 10 full pieces of coursework, I'll let you basically drop two, so you'll only be graded on the 8 best ones that you've actually got across the course. So I hope that will give you a boost, and now you'll be able to just finish off this final third of the course on a high and hopefully really push home those excellent grades that I want you all to get. So there's another assignment which will be set today, which will be due on the 22nd of April. It's relatively easy this week, so we'll get through to that in the laboratory session. In this course today, I'll just be giving you the kind of overall content for a variety of different inferential spatial statistic tests, and then we'll actually be getting into ArcMap on the actual assignment, and you'll be able to run through some of those tests using the spatial statistics toolbox, so it shouldn't be too arduous for you. Let me know if you've got any questions. As ever, it's great to hear from any of you, so if you do have any queries, don't hesitate to reach out to me. I hear from some of you quite regularly, some of you less so don't hesitate to reach out to me if you want to discuss anything. I just want to kind of recap on where we are, because obviously we had that kind of plan in the syllabus where we had those kind of 3/3 of the course. So the first third was essentially the descriptive statistics portion, and then we've just completed the initial inferential statistics part. So that was focusing mainly on a difference of means tests. And then this final third is where we get into some of the really cool inferential statistics tests, which are maybe a little bit more advanced, but really kind of underpin many of the key kind of workhorse statistical tests that you're likely to use in your career. So today we're going to be focusing on inferential spatial statistics, and then the final 2 sessions are going to be on correlation and then regression. So these are some of my favorite techniques, and also some of the most useful for you as you move out into the real world and may actually need to use some of these techniques in order to make sense of the world around you and hopefully make it a better place. So, as we've said already multiple times, we're over here into this part of the course, and I don't think I really need to recap on this too much, other than to say that, we started focusing on descriptive statistics previously, and then moved into the inferential aspects of those statistics, and we also covered the spatial descriptive statistics kind of approach, and here now we're moving and kind of progressing from that into this inferential spatial statistics content. So I think I pretty much said all of this. So yes, we were moving from kind of central tendency and dispersion in those previous cases, whereas now we're starting to say, well, okay, is the data that we've got in our sample, our spatial points or our spatial areas that we've collected data for, has that occurred, pretty much by random, or is there something significantly different from random there? Are we able to say something formal about the world based on there's the kind of confidence level that we would like to be able to say something about the world, which generally is want to be at least 95% certain that the results that we've obtained haven't just occurred at random by chance, which is why we always have that p0.05 probability level that we're looking for when we do actually carry out an inferential spatial test. So spatial patterns, and really these diagrams kind of sum up what I want to demonstrate here, which is that you have on this kind of sliding scale on one end we have clustered data, and at the other we have very dispersed. Okay, so the reason why we're kind of raising this is that when we're focusing on inferential spatial statistics is we're really looking for patterns in the kind of spatial arrangement of points or polygons, but we want to be able to say something formal about those patterns rather than just saying that they exist and that these are the kind of these are the distances between those points. We want to be able to say whether that they have some sort of meaning. Okay, so here we've kind of got clustered over here, which is quite common. For example, if I told you to go off and look at the distribution of shops, retail units, you'll probably find that they are highly clustered. So they're either going to be in the center of a city, maybe in a downtown area where you get lots of shops, or they might be at a strip mall or some area like that. And generally, they kind of cluster together quite well in space. And then kind of the flip reverse of that is, you know, point patterns which are incredibly dispersed. And I was thinking about what a good example of this. And I think actually if you looked at the pattern of farms, if you went out to an incredibly rural area, then you probably find that they are quite dispersed between each other because they need quite a large amount of space in order to either grow crops or to raise your cattle. And therefore you end up with this really quite dispersed pattern between the different farm boundaries, farmhouses, etc. Okay, so we have kind of randomness in the middle here, and then we have dispersed at one end and clustered at the other, and these are kind of examples of which way you might end up getting kind of non-random spatial patterns, okay? So my question, therefore, is do the results, for example, of recent US elections appear to be random, dispersed, or clustered? Okay, so this is from 2008. So this was, I'm trying to think how old I was in 2008. I must have been 20. This was the first US election that I took a really kind of focal interest in. So obviously it was Obama versus McCain. Obama won it in the end. I think McCain was pretty gracious in defeat, though. I guess my question here is, well, do you think that these actual spatial patterns are kind of random, or do you think that they're highly clustered, or do you think that they're dispersed? So, I mean, I think pretty clearly that that they're definitely not dispersed, and I think that they're definitely. I mean, there's a little bit of randomness in certain places, but generally, I would say that, you know, this is really quite clustered, and we're going to start to get into the reason why you end up with these clusters, because basically we've got spatial processes which transcend these relatively artificial boundaries that we've just basically placed on top of different settlement patterns. So here we've got counties, okay? So they are going to be quite small in the New England area, for example, and then as you get out into the southwest, down to the desert area, you've got these absolutely huge areas which still consist of individual counties, even though you know, they could be even 25% of a state, for example. And then this kind of contrasts with those results which we might get if we look at a more recent version. And again, the question here is, well, is it random, dispersed, or clustered? Again, very clustered, but the difference here you'll notice is that we've actually used a much more granular, more fine level of statistical aggregation, and that actually has quite a large impact on the results. So obviously very different voting patterns this time round, particularly if you're looking at the Midwest area and this area, which all flipped towards the Republicans in 2016, Michigan in particular, Wisconsin as well. So essentially, there were these major shifts that took place, which have now somewhat reversed in the most recent election. But the point is that you also have this kind of issue with how you actually aggregate these votes, these data at a more local scale up to something more aggregated, and you know that goes into the issues that we raised earlier in the course around the modifiable areal unit problem and boundary delineation and all of these kind of standard spatial statistical issues, which hopefully when you leave this course and you go off into the real world, you'll be able to critically think about the statistics that are being presented to you in some sort of spatial framework, because you understand those key concepts which are just so important for you to be able to actually interrogate certain results that may be put in front of you on your desk one day. Okay? So, spatial autocorrelation. So this is really kind of the process that I'm wanting to demonstrate to you by showing these different maps and showing how these processes really transcend the kind of artificial spatial boundaries that we place on top of each other. So spatial autocorrelation is a measure showing how much a spatially arranged variable is correlated to itself through space, and it kind of very much builds off Waldo Tobler's first law of geography. So everything is related to everything else, but near things are much more related than distant things. Okay, so this underpins geography and pretty much everything that we do, and it's both a hindrance in some analyses as a result of the things I've just raised before in the previous maps, but also it can be something which we use to our favour in some instances if, for example, we need to interpolate data where we don't have individual points, but we know that there's this level of spatial correlation. We can use that to our advantage in order to try to estimate what the data may be in a place where we have a data gap. Okay, so Waldo Tobler may come up in many of your other classes. I think he ended his days out at University of California, Santa Barbara, so very good geography department out there focusing on nicely spatial, heavily quantitative spatial science. But if you get a chance to go out and visit, I thoroughly recommend it. You know, you've got sun, sea, vineyards, good food, nice pace of life out there in Santa Barbara. So definitely worth the trip. Okay, so this aspect of spatial autocorrelation can be demonstrated quite nicely if we then just randomize certain kind of maps that are well known to us. Okay, so for example, here on the left-hand side, we've actually got the population density of the United States. So we've got the distribution of the population. And you can see it's highly spatially autocorrelated. And one of the reasons for that is, you know, in this case, it's predominantly because of the migratory trends that ended up leading to that population density outcome. Okay, so for the last 400 years, we've had predominantly European descent people basically moving across the ocean to the eastern seaboard, and then people eventually ended up moving westward, which obviously had some negative impacts quite significantly for the Native American people who lived on that land prior. But as those people moved westward, essentially the population increased across that area in order to kind of use up those resources in different ways. But obviously you then have this kind of big gap around the Rockies where there isn't much, and that's because, you know, there aren't that many people in those areas until you basically start to get out to the west coast. And the west coast obviously had a huge population boom at the end of the Second World War, mainly because a lot of the people, mainly young men essentially, who were taken from the traditional kind of industrial heartlands of the USA in the Northeast predominantly were taken to fight in the Pacific. But when they came back in 1945, a lot of them kind of opened their eyes to California and ended up staying there because obviously better weather, more space, and you know, it's more attractive potentially than moving back to some of the places that might exist in the Northeast. Okay, so that's kind of the reason why we have this spatial autocorrelation pattern for population density. We know that kind of based on the kind of history and the trajectory and the evolution of people and the population as they moved across this huge country. But then we kind of contrast it here on the right-hand side to what would happen if we just basically had randomly distributed population density. And you can see that it's quite significantly different from that. So on the right-hand side here, it looks, you know, there's no coherent relationship between the population density levels of all of these different, I think these are also counties again. Whereas on the left-hand side, you have really quite strong autocorrelation, so very high population density in those areas, particularly in the New England area, all the way down to Florida, and then particularly in that California area as well. So areas that are going to be close together are going to have quite similar population densities, okay? And then we can kind of look at this next set of maps in kind of a similar way, and it kind of gives you a bit of an explanation as to why there aren't so many people in those kind of western areas, particularly around the Rockies. You know, maybe Colorado area is a kind of an exception to that, where you've got quite high population density and quite irregular mountainous terrain. But then for the rest of that kind of mountain range there, it's definitely less fertile soil than many of the other places that you might have, particularly along the eastern seaboard and down into the Gulf of Mexico. So that's kind of what that's what the relief map looks like if we look at the digital elevation model for the US. And then if we compare that to the right-hand side, where we just have this very highly pixelated image, where if we just randomly jumbled all of these points, that's essentially what we would end up with. So my point of using this map is just to demonstrate that the processes that we understand that kind of drive our whole understanding of the society and the economy are very much spatially autocorrelated, whether that's population settlement patterns or whether that's down to the actual terrain upon which we exist. Okay. So spatial autocorrelation, much like just normal correlation, can be positive, it can be negative, or it can be zero. So positive spatial autocorrelation means that things that are near to each other are going to be very similar. So that's very much like what we just saw in the previous maps for population density or for elevation. And then that kind of contrasts with negative spatial autocorrelation, which essentially means that things that are close to each other are generally very different. Okay, and then we could have a kind of zero pattern. This is quite probable as well. Sorry, the light bulb above my head is making a noise. So this is quite probable as well. I come across this quite regularly, no spatial autocorrelation, so random patterns. Also frequently encounter positive spatial autocorrelation issues as well. Negative spatial autocorrelation issues. I don't know if I've encountered these that often. I'm still struggling to think of an example to give you of where this might occur. So I might have to do a little bit more research to try and understand where that type of pattern might actually occur. Okay. So there's different ways that we're able to understand this as well. So for example, we've covered a variety of different plots in the other parts of the course. So we've covered different ways for measuring scatter plots, for example. We've covered box and whisker diagrams. And now I'm introducing this concept of a variogram. Okay, so this is basically a scatter plot where we actually have the distance plotted on the x-axis in this case, and then we have the degree of similarity or the degree of variance plotted on the y-axis. Okay, and we're able to plot a line of best fit for the actual points that we're able to measure on this scatter plot, and use it to understand how distance may affect the level of similarity or dissimilarity between whatever it is that we're measuring. Okay, so we have more of a theoretical version up here, which just gives you the general overview, and we're able to note 3 items of importance. So we have the nugget here, which is the uncertainty when measuring locations close to each other, and that can be random variation basically, which leads to that degree. We also have the range here, which is basically the amount, so it's the distance at which differences in attributes no longer correlated. Okay, so we can see that we have this flat line up here where the variance starts to become static, and that's around here at 25 in terms of 25, whatever distance this is, kilometers. And then we have the still as well, so the variance at which the distance and the attribute are no longer correlated. Okay, so that's just this this distance here up to this point on the y-axis. So that's all very theoretical, and I want to give you an example, and this one is actually out of the book, and I think it makes more sense. So for example, we have distance down here on the x-axis, and we have the level of community dissimilarity on the y-axis. So if we're down here at the bottom of this dissimilarity measure, it means that the communities there are more similar. Whereas if we're at the top of this dissimilarity measure, it means that they are less similar and that they're more different. Okay, so when we do that, we can see that as we move from about 10 meters all the way up to about 200 meters, we can see that the communities become more dissimilar as we do that. And then after this point here, so this is the sill point, there is, the further you move away, there will be very little change in the level of community dissimilarity. The reason why you need to understand this is that if we're doing what I mentioned before, for example, we wanted to interpolate data values that we don't have, and we thought we could use the level of spatial autocorrelation as a way to understand this. It's giving you an indication that after this point, you might not be able to interpolate with any level of accuracy in the future. Okay, so you need to kind of be aware of how this pattern changes over space. It also might be the case that you're running more complicated spatial statistical tests, for example, spatially spatially weighted regression, and you might need to understand something about how much this pattern moves if you get into those types of statistical tests where you try to correct for these autocorrelation issues. So why does it matter? Well, as I just said, if we want to interpolate on a surface, then we need to understand this particular process. So that might be something which some of you might do. So kriging is one example of a spatial interpolation method which I was taught when I was doing my PhD. I haven't personally used it very much, but there's a big field of literature in that area which kind of focuses on that, and particularly if you're working in the kind of physical geography areas, then maybe that's a tool which you might want to make use of more frequently. And there are also issues, which I mentioned before as kind of downsides of having data with these autocorrelation issues. And that's because when we do regressions, for example, which we'll be getting to later in this term, there's assumptions, like many of the assumptions of the tests that we've covered so far, that basically those data points are actually independent of each other. And the reality is that if they're spatially autocorrelated, then they are not independent of each other. They're actually highly related to each other, and therefore this not only would invalidate your regression test if you breach this assumption, but you also, you would end up with completely junk results, and that's a significant issue. Your coefficients in that regression would overinflate, and basically you would just end up with nonsense results. And the worst thing about that is that you could see an effect which actually isn't there, and therefore that would be potentially a significant error. Reputational damage could easily ensue. Okay, so we could understand spatial structure or spatial processes by using this factor of interest, okay? And we're able to measure this both at a local level but also globally across an entire data set. So neighbour analysis is a way in which we're then able to understand if different geographical entities are actually neighbours or not. So just kind of moving on from spatial autocorrelation, now imagine that we just have a set of spatial points or a set of spatial areas, and we want to understand the level to which there are neighbours within those certain data points that we have. Okay, so we could be interested in those items that are adjacent to each other, so entities and neighbours basically share a common border, for example, if these are polygons, not points. So we might be able to specifically measure that. Or we could understand some sort of distant threshold, so we could actually measure if entities are neighbours if they were within some sort of distance of each other. This is something which I use on a daily basis. So if I, at the moment I'm doing this project in Peru where I'm designing wireless backhaul networks, so basically cell tower networks to basically provide internet access to people in really hard to reach areas. And I'm doing all this spatial processing, and I always have to, I quite frequently have to add little buffers to these polygons in order to kind of capture things that are close by to them, maybe within some sort of radius that we think we're able to serve with a particular asset that we want to build. And that's why these kind of distance thresholds are relatively useful. You can capture people or other assets that you might want to get within space. So I'm always using these types of threshold values in order to try and do some spatial processing that's relevant to a problem that I'm working on. Okay, inverse distance weighting, that's fairly straightforward. That's just basically reversing the distance in order to understand the spatial distance between different entities, okay? So now let's move into point pattern analysis. So a lot of this content that we're covering here is relatively high level. It's more kind of the theory, and then we'll actually get into the nuts and bolts of how we do some of this in the laboratory session when we pull our ArcMap. So point pattern analyses are global in their approach, and there's multiple different methods that we've already kind of covered at various points within the course. So nearest neighbour analysis is a formalised way for us to understand the spacing of different points. And then quadrat analysis. So we've already covered this within sampling various other points of the course. So what's the overall nature of the points? And we have formal statistical methods that we're able to use in order to analyse these different potential spatial processes when we have this data in these particular point-based ways. So in both cases, we are essentially trying to determine if the pattern that we've actually received has just occurred at random or whether it's significantly different from what we would just expect to take place. Okay, so we've covered previously the fact that many of these random processes can be captured quite well spatially and temporally by a Poisson probability distribution. So we covered that in the previous part of the course when we focused on probability and actually probability distributions. And actually one area where my own work focuses a lot on this is actually designing cellular networks, and basically you can use a Poisson distribution in order to understand how many people may actually take calls or access data within any sort of specific spatial area over some sort of temporal time frame, and that provides us with a way to kind of quantify the demand that may be placed on a network that we then need to engineer and actually build in order to provide decent internet connectivity to people so that they can access stuff either for work, for employment, or for social purposes. So how do we do the nearest neighbor analysis? Well, you have more information within the book which you need to read, so this week's chapter which will accompany this. So if you look at chapter 14 and 15, I think that covers point patterns and area patterns. So this particular question is on this example is on page 211 in McGrew et al. And the objective really is just to determine if a point pattern is a random process, and then we have a set of assumptions that we have to meet. Okay, so these should be relatively familiar to you. We basically need to make sure that we have random sample points. That's been fairly common across all of the different tests that we've used, and we need those points to actually be independently selected. Okay. The hypotheses for this particular approach is that basically the mean nearest neighbor distance here is actually equal to what we would just randomly expect to occur. Okay, so the mean nearest neighbor distance at random. So we have here the random mean NND R, so R is for random, and we've got the bar here indicating it's a mean, and we've got the observed mean nearest neighbor distance here, the NND with the bar. Okay, so that indicates what we would get in the null hypothesis situation, the kind of business as usual status quo, and that's that there's no difference between what we have and just randomly occurring data points. And then for the alternative hypothesis, obviously we end up with the difference, and we're not going to say which way that is. Okay, so this is two-tailed. We're just saying that the data that we have observed have a significantly different mean nearest neighbor distance to what would just randomly occur. Okay, and we could even be more specific if we thought we had some sort of a priori knowledge about which direction that actual effect may run. So we could say that for one alternative hypothesis, the observed nearest neighbor distance that we have is actually larger than what we would expect to occur at random, or the vice versa of that would be that we would potentially expect the observed mean value that we obtain to be smaller than what we would just expect to occur at random. Okay, so we basically need to get this this mean value over here for the random quantity and the observed quantity, subtract the NNDR from the NND for the numerator, and then we need to divide it by the standard error of the mean for the nearest neighbor distance. And that gives us this Zn test statistic. Okay, so it's a relatively simple equation, even if it's a bit more complicated to work out one of these, each of these individual components. But generally, this approach here is analogous to how we compared observed frequency distributions to perfectly normal frequency distributions in some of the previous inferential statistical tests that we've covered earlier, maybe only 3 or 4 weeks ago, where we focused on quite similar tests to the one that we're focusing on here. It's just that this one is spatial. So we need to actually determine the nearest neighbor distance. So how do we do that? Well, we need to get the Euclidean distance, so this can be relatively easily carried out. So you can measure that within ArcMap if you wanted to. Actually, to be fair, in ArcMap it pretty much does it all for you, so it's very, very simple, very, very easy for you to calculate this stuff. And the way that I approach it normally is I sometimes have to code a lot of this by hand, so I would iterate through all of the different geometries for all the different points and basically measure the distance between each of those in some sort of projected coordinate reference system format. And that would just give me a set of maybe list results which details the distance between each of them. And then I could use that in order to run through this relatively simple set of equations. So if any of you are thinking of moving on to that more kind of programming, computer science-based spatial analysis kind of approach, don't hesitate to reach out to me if you're interested in doing some of that in future research. So we're working on a variety of different projects right now. So from working out how to develop a landing system for Mars, so you know where to best land your spacecraft if you need to. So we're also working on a paper where if there was maybe a runway blocked at Dulles or at Manassas Airport, we actually had a backup recommending system basically for where planes may be able to land if the normal traditional runway is blocked, and we're able to use a variety of different ways to kind of measure that, and some of these kind of spatial processing techniques can be used to inform that decision among a whole load of different data layers that we actually plug in. Okay, so that's kind of some of the more fun applications for these techniques that we're actually applying right now, which is very exciting. Because if you get one of those and it's turned into a real world recommender system that could save people's lives, it's great to have that kind of real world impact with the research that you do. Okay, that's enough of that. Let's get on to these equations. So we can calculate the nearest neighbour distance. That's relatively straightforward. We can then calculate the mean nearest neighbour distance. So imagine we had that long list of all the distances. We can just sum that, so we get the total distance and divide it by the number of samples that we've got in the data set, and that gives us the mean nearest neighbour distance. We can then calculate the mean nearest neighbour distance for a random pattern. So basically here what we're doing is we are just assuming that those data points have a mean distribution, a fairly average distance between them. So you have to exogenously state the area of assessment that you're working on. And then basically this will just pretty easily calculate what the kind of the mean distance would be if we just had randomly distributed points. And then we can get the standard error down here for the nearest neighbour distance test. So we have to basically use this numerator of 0.26136, and then we just need to get the denominator here, which is the square root of the number of samples multiplied by the number of samples over the area. Okay, so this should be relatively analogous to the normal standard error of the mean that we've covered in those previous tests. Okay, so I don't think that anything here is kind of too complicated for you, I think, because we've already covered some pretty nasty equations in some of the other cases, so this should be relatively straightforward for you to kind of comprehend and understand, I hope. So this is an absolute measure, it's not relative, so basically the result that we get is going to be in the underlying units that we actually use. So ideally, meters is what we should all be using to actually measure these distances, hopefully. So metric units are going to be the kind of standard way to do science. I should really dig out that video, but there were some problems previously of converting between imperial and metric units, which led to a variety of crashes in space from various rocket tests. And now I think everything is just done in metric. There are no imperial to metric conversions because it introduces all of these potential errors which you just don't want to have to deal with. So if I can get one thing through to you from this course, it's that science is done in metric units. So it's definitely worth you always prioritizing that type of unit for when you're doing this type of research in the future. Okay, so these are absolute measures. You can also use a standardized nearest neighbor index. So that's basically where we take the ratio of the mean nearest neighbor distance to the random nearest neighbor distance, and we end up with a set of R values. So 0 is perfectly clustered, 2.149 is perfectly dispersed, and 1 would just be totally random. So we can kind of think of this as a descriptive spatial statistic, okay? It's nice to have these kind of standardized metrics at times if you have to unfortunately measure the kind of variation between data sets which are in different units, and it's not that easy for you to kind of convert between those units, then this is one way in which you can do that, okay? You can get the R value down here just by taking these two units. Okay, so if we had those R units, so 2.149 down here would look a lot like my cell tower configuration. These are, they look like triangles, but actually you can think of them as hexagons as well if you want. So these are just perfectly geometrically spaced points across space. And then in contrast, you've got this R value down here of 0.5, where we actually have these highly clustered points here. And then we've got something of 125 just over here. So it's a bit more dispersed than just random, and it's kind of an intermediary between these other outcomes that we've got here. Okay. So the importance of area, and actually you might have caught me saying that in the previous formulae that I gave you, because I did mention that you had to provide an area in order to calculate that random distribution factor. So this is something that you're going to need to consider. It means that you may need some sort of polygon study area depending on what your problem is. So that could be a city boundary, county, state, country, etc. Whatever you want to use to define your problem that you're studying. And then if you've got no formal or logical boundary, then you need to designate one, which obviously introduces additional issues because, whenever you impose a boundary on something, you're going to be encountering all of those boundary delineation issues or modifiable areal unit problem issues that we've already raised at previous points of the course. So now let's move on to quadrat analysis. So obviously we've covered quadrats previously, so just imagine equally spaced squares that we might have in some sort of template that we want to place on top of an area. So theoretically, for example, we often divide areas up. Actually, it's probably more applied, but we often divide areas up to estimate what the population density may be. So I use a lot of maps that are 1 kilometre squared population density estimates for the whole world. And you can think of each one of those squares, if you want, as a quadrat. But equally, from a more kind of historical perspective, when I was an undergrad, I was in applied science, and we'd go out and we were doing a field course, and we were given basically like a metal frame that had 16 squares in it, and that's actually a quadrat, this kind of physical object that you would have. And we'd go out and measure species distribution across ecosystems. So you kind of get this grid and you throw it in the air, and it would just randomly land somewhere, and you go over there and you count all the different species that were in each one of the quadrats, and then you'd be kind of made to go off and do that 400 times in a day, and you end up with a data sample that then you're able to do further analysis on. Okay, so I won't be sending you out to do field trips, but that's kind of the thing that first year undergrads should probably be put through their paces to go out and do things like that. Okay, so quadrats, hopefully you know now, we have these requirements. So we need to have a random sample of points. We need them to be independently sampled. And here what we're doing is we're trying to measure the variance mean ratio, okay? So the null hypothesis is that the variance mean ratio is equal to 1, and the alternative hypothesis is that it's not equal to 1, okay? So we could have some sort of direction on that hypothesis if we need one, if we have some sort of a priori understanding. Maybe we think it's more clustered or more dispersed, whatever. But what we want to get is the chi-squared statistic, okay? So to get the chi-squared statistic in this case, it's just a function of the variance mean ratio and the number of cells that we have, okay? So we're focusing on the frequency of occurrence of these points in the quadrats rather than the spacing of the points, okay? So that's a kind of limitation of this particular approach. As I mentioned before, the quadrat is a series of regularly sized square cells. That shouldn't be new to you. Okay, and we're able to understand if the actual distribution of points that we have is relatively random, or if it is significantly different from that maybe random Poisson process. Okay, so up here we have an example of perfectly dispersed data with no variance. In the second case here we have highly clustered data with large variance. And down here in the third case we just have random data with only moderate variance. Okay. So the variance mean ratio, how do we actually calculate that standardized variability metric for all of the cell frequencies? So what we need to do is we need to get the variance mean ratio, and we need to do that, we need the variance of the cell frequencies and the mean cell frequencies, okay? So we can see that it's this very simple equation here. We just need the variance of the cells as the numerator, and we need the mean cell frequency as the denominator, and that gives us the variance mean ratio. The only hard part, I think, is just getting this VAR metric here. So it does mean that we will need the frequency of cells, F, the number of points in the cell, so X, and then the number of cells, M, and the number of points, N. And actually, to do that, we need to take the sum of the F of X, and then we need to subtract the product of this these square brackets just here, and then divide it by the number of degrees of freedom, and that gives us our VAR, our variance of cell frequencies, okay? And then to get the mean, that's relatively straightforward because we just need the number of cells and the number of points, so just divide the number of points by the number of cells, and that gives us the mean number. Okay, a few extras. So the number of degrees of freedom that chi-squared has is n-1 for this test. Okay, well, that's nothing new. The modifiable areal unit problem is always a problem. Yeah, so as I've said, you need to think about how your spatial process is actually distributed, and then you need to have some sort of logic to determine which spatial level of aggregation you're going to use. And this used to really freak me out when I was an undergraduate, because there's no hard and fast rule how to do this, and it's going to depend on the results that you get. So, you know, that comes with experience. It also, I think, having confidence as you get older also helps. You just have to pick something that you think reasonably represents the process that you're studying. So I think actually a good way is to look at the past literature and see what they've done there. Then you can always cite the other people who did it before you, and then kind of a lot of that burden is kind of off you, and it's kind of linked back into the literature as being a sensible decision. Okay, so that's for quadrat size, and I think also for the way that we think about actually carrying this process out. I think what's important down here as well is it also identifies the fact that we're just counting the number of points within the quadrats. So these two here have very different spatial outcomes, but they would end up with the same results because they've got the same number of points in each quadrat. So that's quite significantly different from some of the other tests, maybe, which might be able to capture more of that nuance. We just covered points. Now we're going to cover area patterns, okay? So it's quite similar, it's just that rather than using just points or coordinates of x, y, individual points, we're going to be using areas. So that's just more than two sets of coordinates. So a polygon it has to be 3 or more, basically. Actual points in order for you to make a polygon. And once we've got those, we're able to then actually do some interesting analysis for those polygon points. Okay, so polygon shapes. So what we're going to do is we're going to look at the join count analysis here, and also Moran's eye. They're a little bit more complicated. Actually, they're quite a bit more complicated, but we'll do a lot of this within ArcMap, and it will do the heavy lifting for us. So you're just going to have to bear with me while we go through the kind of nuts and bolts of what this is done. Don't worry, I won't be making you do this in the laboratory session like we were doing in R with the other tests. So for the join count analysis, here we're focusing on basically binary outcomes, binary categories, so they're either joined or they're not joined, okay? So it's just either or. So the point is to determine if a random process has generated a binary area pattern. To do this, we obviously have to have polygons which are assigned to one of two categories, okay? So traditionally this is done, you know, just by thinking as you would have a black and white photo. Here we're just having a black or white outcome colors, essentially. So we have areas that can be assigned to one of two particular outcomes. We need a consistent methodology for determining adjacent and non-adjacent pairs of areas, okay? So if we have the null hypothesis here, that would be assuming that basically the observed joins of our black and white polygon area, so this is the way that it's traditionally done within the literature, is basically equal to the expected number of joins that we would have between those polygon black and white areas, okay? So the alternative hypothesis obviously would be that there's some sort of significant difference here. So they're quite significantly different, and it could be that that's two-tailed, so we don't know whether it's larger or smaller, or we could have an alternative hypothesis that's kind of directional, so one-tailed, so more dispersed or more clustered, whatever. Once we've got those, once we're actually able to calculate the expected and the observed black and white joins, the way that we get the ZB test statistic is just subtracting the EBW from the OBW and dividing by the standard error of the black and white joins. And it is more complicated to calculate these individual inputs. So this is nice and easy, this one equation here, but actually, particularly to get the standard error of the black and white joins, it's a pretty horrendous equation, I'm afraid, a bit of a monster. So in the join count analysis, this is basically where we have a shared border or an edge that's considered a join. This is not the same as when we're joining polygon areas in GIS, and maybe we're trying to join spatially and pass information between different types of geometric shapes. This is not what we're doing here. The aerial data is categorized in that binary distribution, which I explained before. So classical practice is to call one group black and one group white, count how many are black-black joins or white-white joins or black or white joins, and how many are similar and dissimilar, and then understand how many, the outcome, whether it's clustered or dispersed. So I think that should be reasonably okay for you. How do we obtain the desired sample data to determine the expected number of black and white joins? Well, we can use a variety of different types of sampling. So we could use free sampling. So that's one approach where we determine the probability of the area being either black or white, depending on the kind of expected outcome. So the theoretical models of reference from the literature, for example, given some sort of geographic scale that we're working within. And then there could just be non-free sampling as well. So that's where we only use the study area that we've actually got data for. That data is sampled to generate expected counts. So generally what we're going to be doing is using kind of non-free sampling methods within our kind of general approach that's more common. So here we're getting into the really horrendous equations, I'm afraid. So to do the join count analysis, we basically need to get the OBW value I spoke about before, so the count number of the observed black and white joins, and then we need to get the expected number that would just randomly occur by chance, okay? And the way that we're able to do that for the EBW is to basically take the number of joins that we have. So I'm just looking at the actual equation inputs down here. So J is the number of joins, B is the number of black areas, W is the number of white areas, N is the total number of the areas, so it's the black plus the white, and L is the number of links, okay? So to get the EBW, we can multiply 2 by the number of joins, by the number of black areas, by the number of white areas to get the numerator. And then to get the denominator, it's just the number of samples that we've got multiplied by the number of degrees of freedom of the sample, okay? So that's reasonably okay, nice and straightforward. Now we'll move into the standard error of black and white joins. And actually it looks horrendous, but it's a lot easier than you think it is, because actually it's a square root, okay, fine, but then we have this EBW here at the beginning, and we have the EBW squared here, which we subtract at the end, and therefore we only have these two terms in the middle, therefore, to work out. So once we put it that way, it's a lot more straightforward, I think. And you are also able to follow this along within the book. So, for example, if you're interested in looking, we have this nice example on page 225. I think I already quoted that page number for you. Oh, it starts on 223. Okay, yeah, so 223 is where you get the kind of general qualitative background that's presented. And then we actually have an example here. So for the join count analysis, starting on 225, and it runs through to page 228, okay? So you should be able to read it in here, look at what I'm doing, and hopefully then that kind of cements into your own mind exactly what we're doing here. But it's not as complicated as it looks. So this is a horrendous amount of information, but do not be intimidated, because all we're doing is we're literally doing something very similar to what's in the book, but I created an even more simple way to, even simpler way to kind of understand it, and that's that we just have these 6 polygon areas here. Okay, so we have, so I didn't put these in black and white because then this way they actually match the color scheme for the presentation. So just assume this dark mason green is actually black and the white is white. Okay, so we have these 4 polygon areas that are black, and we have these 2 polygon areas that are white. And then we just need to count the joins that we have. So we have 1, 2, 3, 4, 5, 6, 7 joins for these very simple 6 polygons here. Okay, so if we look over here, we actually have the joins. We have 7. We have the number that are black, obviously that's 1, 2, 3, 4. The number that are white, which is 1, 2. And we have the total number of samples, which is just the black plus the white. Okay, so that's 6 in total, 4 plus 2. So very simple. Then we need to get this, this L, this is the sum of L multiplied by L minus 1, okay? So there's a way for you to kind of understand what we're doing here. If you go to page, so table 15.3, which is in page 227. Or what I did very simply, just to show you exactly what we're doing here, is I just tapped it out. So obviously we have those 6 different polygons, and then 4 of them have 2 joins and 2 of them have 3 joins. Okay, so these are the number of links that we have, L. And then to get the L minus 1, it is just literally the A2 value here minus 1 all the way down. So then we end up with this L and this L minus 1, and then all we need to do to get this outcome here is just the L values multiplied by the L minus 1 values, which gives us 4 2s and 2 6s. So what we end up with is 20. Okay, so 20 is, in this very simplified case, the sum for the L values. Okay, so they also show that in the book, which you can take a look at. Hopefully that's clear for you to see. So I've given you the Excel demonstration, and I've shown you where in the book you need to look to understand that. Okay, so we need to get the observed number of black and white. So the observed number here is 4. And the expected number here we need to actually calculate, so we need to go back through that equation. And when we do, so we've covered this already, so I'm not going to go through it again, we end up with 3.73, okay, for the EBW factor here. So we've basically already got, if we look down here at the Z equals OBW minus EBW divided by the SBW, we've already got both of the numerator terms, so 4 minus 3.73. Okay, so we just need to get that bottom denominator input for this particular equation, then we're done. So that's how we get this horrendous equation. So we have the sigma BW here. We need to take the square root and then just tap into this equation what we have. So the square root's pretty easy, and then we can just slot in that EBW that we calculated up here. So 3.73 at both ends. Obviously this one's actually squared as well. Then we can get started over here. So we know that we have 20 for this L multiplied by L minus 1, the sum of. And then we need to take the B and the W terms here. So that's 4 and 2. And then for the denominator, we just need the number of samples multiplied by the number of degrees of freedom. So 6 multiplied by 5. So that's fairly straightforward. And actually, I'm not going to run through each of these, but if you just run through it, very simply, it's not hard, it's just long. So it's just, I always explain that when my father taught me to read, he taught me to look at the really long words and then kind of break down by syllable the word into bits that I could easily pronounce. And actually this math is just exactly the same. Just break it down to really easy components, and that's why there's multiple different steps here. So hopefully by the time you get to this step here, it's reasonably straightforward in order to just carry out this particular calculation. And rather ridiculously, after all of that, we end up with 1 as the actual outcome. So we can put that in as the denominator into our equation, and what we get is a value of 0.27 for our z-score, which is obviously very low, which only gives us a p-value of 0.4. So we failed to reject the null hypothesis based on this particular example. So that was quite a lot of work just to get that one outcome. Thankfully, you'll be glad to hear that this is pretty much all done for you within the programs that we're going to use in the lab. So I've explained how we do it at a high level, and then hopefully we'll be able to run through it in simpler terms in the laboratory session. Great, so we're on the home straight here. I'm going to have you done in the next 10 minutes, and then you can go off and take a break before the lab session. So essentially, we mentioned about Moran's eye previously. So this is an example here of the global assessment of spatial patterns. So you can follow this in McGrew. There's a good example in there, page 229. The objective, obviously, is to identify non-random spatial patterns. The requirements that we have, so we have a minimum number of 30 geographic features that need to be inputted into this particular equation. We need attributes that are essentially ordinal, interval, or ratio. And then we're able to specify some hypotheses. So for the null hypothesis, the attribute values are essentially randomly distributed. So that's our business as usual kind of standard-based approach to this. Whereas the alternative hypothesis, we're essentially saying that these values are not randomly distributed, okay? We're looking for Moran's eye as the test statistic, and the way to do that is basically to run through this equation here. So I've broken it down for you, so I have the number of areas here, n, and then what we have is the sum of the crossed products for all of the contiguous pairs for I and j. Okay, so don't worry, we'll run through what this means as we go through, and actually for Moran's eye, I'm not going to make you calculate it by hand because it gets more complicated, but you do just need to know what goes into those test statistics that we're going to be using. Then on the denominator, we need the number of joins, and then we need the variance of the area attribute values, okay? So Moran's eye takes into account actual attribute values to determine if these values are random, clustered, or dispersed. They can be used on both points and areas, and we need to determine the neighbours within our particular sample. Okay, so generally contiguous regions, but we can also use inverse distance weighting if we need to. So I think the point is that if the Moran's eye that we get is -1, then we would have perfectly clustered dissimilar values. And then if it's 0, that's basically perfect randomness. There's no autocorrelation. This is kind of good if you're running regressions, because then you don't have to worry about spatial autocorrelation. Or if it's +1, you know, or strongly positive, then we would end up with quite strong clustering of similar values. Okay. So Moran's eye, how do we calculate that? So once we get the eye, we're able to just subtract this EI value here, so the expected value, which is -1, divided by the number of degrees of freedom, and that gets us our numerator value here. And then for the denominator, we just need the square root of var I, which is complicated to calculate. So in this case, GIS, ArcMap GIS is going to do it for us. But that gives us the z-score that we want, and then we're able to treat it as any other z-score that we've been assessing this term, okay? So we can get a p-value for that z-score depending on where it actually sits within the distribution, which is able to tell us something important about the level of randomness or non-randomness within the data that we have. Okay, so we're able to, as I say, assess the level of autocorrelation in a certain data set, use it to find hotspots of autocorrelated values. So if I was to rerun this, if I was going to rerun this over for the different election maps that I was showing before, I think we get quite interesting results for the degree of hotspots for different voting patterns, which is quite interesting to understand. Formulas relatively similar for global measures that we can, so we have these global and these local measures that we're able to assess. So here we're focusing more on the local assessment part. Before we were focusing more on the global part. But we can run these and it will help us understand differences between different areas. So here's an example of residential segregation So David Wong, who's within the department here, a lot of his work in the past has focused on neighborhood segregation, particularly in the United States, particularly in terms of application, but also in terms of developing statistics that help us to understand this. Okay, so you can see there's really quite strong segregation, sadly, in Detroit here, between its racial segregation, between these areas, so across, I guess this is the wider city area. We're able to, as a consequence, for those different categories that we've got, actually run this spatial autocorrelation report. So we're able to do this, for example, within ArcMap, and then assess the scores that we get. And when we do that, and we run the global Moran's I for all of these individual data points, we end up with an incredibly high Moran's I. So it's 0.88. So remember that 1 was kind of perfectly clustered values, so this is incredibly strong. The z-score here is 48.26, incredibly high, so we had a p-value of 0.00000, highly significant results. Okay, so this is one way in which we're able to assess these different spatial patterns, in this case obviously with incredibly strong level of spatial autocorrelation. That was at the global level, I believe. So now we're focusing on the local level. So for locals Moran, we're able to actually look at specific clusters, okay, and where we maybe are able to find significant differences relative to the level of the observed variation that we might have. Okay, so this is just providing you with a Moran scatter plot here. So we're able to understand how the classification of different spatial associations for these 4 different categories that we have actually corresponds to the location of the points in our plots. So these categories are for high, low, low, high, or high, low relative to the mean, okay, which is the center of the graph. So this is basically how we're able to carry out this local Moran's I analysis. So we will get into this in the laboratory session. I think what's nice about this is actually projecting back onto the map, so you get like a nice way to understand which areas are significantly similar or dissimilar. So everywhere in grey isn't similar, and then everywhere in either black or blue here are highly significant findings that we actually have. Okay, great. So I won't take more of your time. I think that should be a reasonably okay overview of all the different inferential spatial statistics tests that we've covered, that we are covering for this particular course. You've got the McGrew et al. Book, so you can go off and you can have a look at that if you need any further clarification. If not, then I'll see you in the laboratory session. Hopefully we'll be able to kind of translate some of this more kind of high-level insight into actually developing some nice results for some actual analyses. Great, so thanks for tuning in, and I'll see you all soon. Goodbye.